Hello. Ever get into one of those situations where something in life happens, like your car breaks down and then you spend an entire week trying to get it all sorted? Well, that's what happened to me. I wanted to make this video last week. So, when I was working on various ways to calculate celestial objects, particularly the stars, I got to thinking that I got to the answer originally using a software like StarWalk. It's nice and all, but what happens if you don't have access to StarWalk? Is there a way that you can do it in a very low tech sort of way? And let me just describe briefly how stars are located in the sky. So we know that the Earth rotates on its axis, and we know that it also rotates around the sun. So one revolution on its axis is 23 hours and a little bit, but because the Earth moves slightly away, the Earth has to rotate a little bit more than 360 degrees to point back towards the sun, so that 24 hours is always going to be local solar noon. So the way the stars are mapped in the sky, from what I understood doing some research, a number of tables produced by a number of people. In this case, this is a small little database of 300 stars about. You can go and find some that have a lot more stars in them, but each star chart should contain a right ascension and a declination. In terms of right ascension, you can think of the right ascension as the longitude. The declination is equivalent to the latitude. Because the Earth rotates on its axis and around the sun, the orientation of the stars will change constantly relative to the Earth. So we have to create a standard as to a particular time and a particular date where the stars are going to be located in the sky. So here I've got the year 2000. Let's say that the Earth is directly in line between the sun and this particular star. Whoever sees local solar noon at that particular moment in time, somebody on the opposite side of the world will see that star reach its zenith at the same time. The Earth does not rotate around the Sun after having revolved on its axis exactly 365 times in a year. We have to add an extra day every 4 years to bring the Earth back into the same celestial alignment. In just 1 year, the Earth won't be up here anymore. It'll be down here after having revolved around the Sun, not having returned back to its initial starting position the year earlier. So in just 1 year, let's say that this is Greenwich Mean Time, 12 p.m., and this is longitude 180, midnight. Then the next year, 2001, if this is 12 p.m., year 2001, same calendar day as this one was in the year 2000, then the same person standing on the other side of the world will no longer see that star having reached its zenith because the Earth is not in the same location anymore. Right ascension and declination of stars are timed to a specific Julian date. So, how does that apply to how I want to use this in a very low tech sort of way? Well, what I did was I found a number of formulas that will generate the Greenwich apparent sidereal time. I think that's what it's called, or sidereal time. So the Greenwich apparent sidereal time is the hour in which, for any particular date and time, that all of the celestial objects have to be adjusted to calculate where the star is going to be in the sky for that particular time. So I took this formula and I created a separate tab in this spreadsheet. And I started with January 1st of 2000 at midnight. And this is all expressed in GMT time. And I use those exact same formulas that I had used in here to generate this value here. So this is really this column over here. I just copied it over here so that each line starting from the year 2000 is January 1st of that year. And this represents the Greenwich apparent sidereal time all the way to 2055. So the next thing that I wanted to do was, once I've got the position for January 1st midnight GMT for the next 50 years, I created a separate table which was the GAST time adjusted for midnight of a particular day in the year 2000 all the way back to 2001. And each one of these is really the GAST time minus the GAST time of the year 2000, which is the starting point for all of these values. So the idea is, if you want to locate a star in the sky, all you need are these columns here to locate which year we're in. So in this case here, we're in the year 2019. So it's going to be this one. And I'm recording this on November 17th. What I decided was to skip every 8 days, and it's good enough an approximation in this case. So we want November 17th, which is going to be these two here. So this is just a spreadsheet that I created to work out all of the math and particularly mark out these 3 steps. So the way it works is we need to calculate the GAST time for that particular day because I don't have a GAST for every single day of the year 2000. So I just approximate it using 16th and the 24th. So if this is the value for 16 and this is the value for 24, what I just did is I just created a small little formula here that will go and calculate the number of days between the 16th and the 24th and find the slope and then go and get the 17th and then calculate what that's supposed to be. So now we can take this one and put it in our day adjust. And so now we have our 2 values. Now, if you're going to do stargazing with this, you would only have to do this once for that particular night, because these here are going to be the only 2 additional calculations you're going to need are going to be these 2 here. So all we do is we add the year adjust and the day adjust. That gives us 3.8349 hours, working out to be 3 hours and 50 minutes and 6 seconds. So that is the estimated Greenwich apparent sidereal time adjustment. Now we need to calculate what is going to be for the local hour. And in this case here, I'm recording this at 3:30 p.m. local time. That's going to be close enough. And what we do is we take, so the local time is going to be represented as 15.5 something. And then we add that to our 3.83, and then we multiply that by 15, and that gives us 209. So that gives us a local hour angle of 290 degrees. Now, at this point, this is still relative to GMT time. And what this does is it will adjust the hour angle of a particular object for our local longitude and our time zone. So now what we do is we take our local hour angle that we calculated, which is represented in degrees, and we add our longitude. So in this case here, we're subtracting 75.3 degrees longitude, and we're subtracting the object's right ascension, and the object's right ascension is going to be for a particular star. So let's say I forget exactly which one I picked, but let's go and say if we want, let's go and pick Betelgeuse. So that's going to be right ascension. So at this point, our object's right ascension is 88 degrees. So we took our 290 and we subtracted our longitude of 75. Well, we added minus 75, which is really subtracting 75. And then we subtract 88. And then we subtract our time zone by 15 degrees. So our time zone in this case is minus 5 hours from GMT. So it's going to be minus 5 times 15, which is going to be minus 75 degrees. So in fact, we're adding 75 degrees. And that works out to the object's hour angle of 201 degrees. Or if we turn that into hours, minutes, and seconds, we divide this value by 15 and then express that in degrees, minutes, and seconds, we get 1327.43. So this formula here is something that I've used in the past to turn the object's right ascension and object's declination into an altitude and an azimuth based on your latitude and your longitude. So at this point, at 3:33 p.m., that is where Betelgeuse should be located. So it should be 33 degrees below horizontal with an azimuth of 26 degrees. At some point, I would like to take these values and create a nice little PDF that somebody could download and have the formulas written in simple steps like this that they could essentially locate any star they want with nothing more than that PDF and a calculator. That's it for now. I hope you enjoyed it. If you did, give it a thumbs up, like, subscribe, all that good YouTube stuff. So I hope you liked it. Bye for now.